Enter the bored piling rig. Its mission, drill 980 boreholes, plunging 86 meters deep into the bedrock. Into these voids, massive cylindrical rebar cages are lowered, forming the tensile backbone of the piles. Once piled, the earth is excavated, creating a 31-meter-deep foundation pit, held back by an impenetrable diaphragm wall.
The mat foundation pour, 60,000 cubic meters of concrete, pumped continuously for 63 hours to prevent cold joints.
The 6-meter-thick raft cures. From this monolithic base, the central structural core, the supercore, begins its vertical ascent. Speed is critical. The slipform system utilizes hydraulic jacks to climb the core, one full floor every 3 days. Pushing concrete against gravity requires monstrous pressure. Specially engineered Putzmeister pumps force the liquid mix vertically up the core. Every pour is scrutinized. The structural engineer verifies the concrete slump and rebar spacing. Tolerance for error is 0. Surrounding the core are 8 megacolumns, massive composite pillars of concrete and steel, bearing the primary vertical load of the tower. Lifting thousands of tons of steel requires the climbing tower crane. Anchored directly to the core, it jacks itself up as the building grows. To resist immense wind shear, they install outrigger trusses. These steel bridges lock the core and columns together, creating a unified rigid skeleton. The rigging team executes the final lock. Using hydraulic torque wrenches, structural joints are bolted with thousands of pounds of pressure. To seal the habitable zones, an inner cylindrical curtain wall is installed. But this is only the first line of defense. With the lateral framing secured, corrugated metal decking is laid down. This acts as the permanent formwork for the composite floor slabs. Extending from the floor slabs are lightweight radial trusses. They reach outward to support the massive, twisting outer skin. As floor upon floor cures, the shape emerges. Not a square box, but an asymmetrical and 20-degree twist. Over 20,000 outer glass panels must be hoisted, each one individually curved, mapped by precise CAD coordinates. Hanging hundreds of meters up, the glazier team carefully guides each 2-ton panel into the extrusion slots. The connections are not rigidly fixed. Flexible struts allow the outer skin to slide and shift independently during seismic activity or typhoons. This dual-layer system creates a massive thermal buffer, an insulating void that drastically reduces the heavy cooling loads of summer. The V-shaped groove running up the facade isn't just aesthetic. It forces wind vortices to break up, reducing lateral structural loads by 24%.
Bring it down right here. Easy now.
Okay, it's set.
Hand me the shovel.
As construction surpasses floor 118, the outer skin stops, exposing an open-air steel lattice crown. Into this wind tunnel, 270 vertical-axis wind turbines are craned into position, capturing the extreme high-altitude gales. Deep inside the peak, a specialized reinforced concrete chamber is cast, engineered to support an active, moving 1,000-ton load. Rejecting traditional hydraulics, engineers install massive copper plates, the foundation for an advanced eddy current magnetic dampener.
August 2013, the final steel beam is bolted. The structural framework successfully tops out at a staggering 632 meters.
The mega skeleton is complete. But a body without a nervous system is just a monument of stone and steel, pulling the copper arteries. Thousands of kilometers of armored electrical cables winched vertically through the core. Pumping electricity 600 meters high causes severe voltage drop. The solution? Installing massive dry-type aerial substations every 20 floors. Transporting those people requires a flawless vertical highway. Steel guide rails are laser-aligned to a tolerance of fractions of a millimeter. At the summit sits the custom-built Mitsubishi traction machine, a mechanical beast with enough torque to hoist a military tank. This is the Bullet, an aerodynamic, pressurized cabin engineered to blast upwards at 20.5 meters per second. Pushing a box up a narrow tube at that velocity creates massive air compression. The fairings literally slice the trapped air. As the cabin rockets up, the high-density steel counterweight plummets. Pure mechanical equilibrium. Back at floor 125, another equilibrium is being engineered, stacking the plates to forge the Iron Heart.
1,000 tons of mass. Suspended mid-air. Beneath the massive weight, technicians bolt down a permanent magnetic array, the core of the eddy current damping system.
There is no physical contact. The 1,000-ton copper plate floats mere millimeters above the magnets. The displacement is exactly as modeled.
Check the cable tension at maximum extension.
As it swings, the copper cuts the magnetic field, generating opposing electrical currents. Frictionless, silent, unstoppable braking.
The electrical veins are pumping. The mechanical heart is armed. The machine is ready to challenge nature. 600 meters up, the air is a weapon. The crown turbines don't fight it, they eat it.
Spinning at high RPMs, 270 turbines generate up to 350,000 kilowatt-hours annually. When the typhoons hit, the facade becomes a catchment area. A vertical river. The rain harvester, siphoning thousands of gallons of stormwater away from the streets, routing it deep into the belly of the beast. Down in the bedrock, massive retention tanks swallow the flood, filtering it, purifying it for the tower's secondary systems. Recycled rainwater pumps life back into the sky, feeding the 14 internal garden sanctuaries without taking a drop from the city.
The HVAC lungs ignite, regulating the internal climate for a volume of space equal to a small town.
Every square meter is wired. A smart grid ceiling regulating lighting, temperature, and occupancy data in real time. Maintaining this glass titan requires a monster of its own, the BMU Spider, a custom-engineered crane system hidden in the crown.
Now, the machine must be wired to live.